I'm going to sidestep talking about compound interest for just a minute. Let's think about if I were to double something every year. And then I guess this makes sense. After 4 years, if I let something double itself, it would be 2 to the 4th power. So this exponent would really just be the number of years. But what if instead something, doubled itself, not every year, but every month? So that it did this for a really long time, until it did it for 48 months. Well, I guess that I can see that if something didn't just double itself for 4 years, but did it for 4 years every single month, and there are 12 months in a year, then I guess I understand, that this would really be to an exponent where it's like the year as well as the frequency with which it happens per year. Now, the point I'm making is sometimes money compounds quarterly, meaning quarter 1, 2, 3, 4. So if I wanted to figure out how much money I would have if I invested $500 and somehow made, decent interest on it, but not just every year, but also every quarter, well then I'd do times 4. But I don't want that to work just for quarters. I want it to work for any number of frequency. So I'm going to call that NT. Okay, I think that can kind of make sense to me. Yeah, so I can kind of picture that. So, something else to think about, though. Let's say this does grow 48 times when you have it happening every month for 4 years. So if this were a bacteria or something, I could maybe see it growing at a rate of 6% every single month. But if you could make money this way, and in 4 years you could end up multiplying your money or increasing your money by 6% every single month for 4 years, and have that happen 48 times, have any idea how outrageously large that would get? Go ahead and type that in. Let's do 500 times 1.06 to the power of 48. That means that for being able to avoid making a selfish purchase of some electronic that you really wanted that was $500, if you just waited 4 years and avoided that one purchase, you could instead have 10 grand. And I know I'm rounding up pretty generously. So to me that seems a little bit outrageous. And the reason it's a little bit outrageous is because, when that happens, usually you have to adjust this percentage as well. So that it's really not good enough to use that original rate that you had. You're probably going to have to also divide that rate out into the total number of times that it's compounding itself. Meaning that if I'm going to make 6%, I'm going to have to divide that by 48 to be a little bit more realistic about it. And so that was my way of hopefully putting some meaning behind this formula, so that we can see that, if I want to deal with and figure out what I have currently, so there's my current amount, my future amount, compounded with whatever this frequency, this is going to be the frequency, this is going to be my rate as a decimal again, and t is the time. So hopefully that helps as we read this definition. A is the current amount, P is the principal, so A meaning where you ended up. I like to think of that as future. P is the principal, the initial amount. R is the annual rate of interest as decimal, and the number of times it is compounded each year. and t is the number of years. First you'd have to figure out which formula to use, but since these notes are set up so that it breaks it apart, you automatically know you're using this one. But let's pretend you didn't know that. So read through the problem. Maria's parents invested $14,000 at 6% per year, and the big tell is that you have this word compounded. And since it says compounded, you're looking for the frequency with which that's going to happen, and I see the word monthly. And from this, you should process that. That means that every single month it'll be rebalanced. So that tells you that n is going to be 12, because there's 12 months in a year. So let's go ahead and plug in these values. The initial investment, or the starting balance, P, is 14,000. I'll rewrite 1 plus, but the interest rate is 6%. And, you know, the way I was talking about this was that if you have 6% and you simply took that to the power of t, that number would get like outrageously large if you did 10 times 12. So that's why this 6% would be broken down over the 12 months that it happens over. So I plugged in the r, which was the percent as a decimal. I plugged in n, which was driven by the monthly changes. With this in place, now you're going to raise it to the power of nt, which would be 12 times 10. And then notice that all of this is in the exponent, meaning that this 120 value is going to be your new exponent. So I'll do this in a couple steps. 14,000, and then 0.06 divided by 12 is 0.005 to the power of 120. And I should have kept that in a color that you do normally write. Now let me point something out. This is really just increasing by really 0.5%, because that's where this decimal place is at. And that's significant to note because, you know, 0.5% would be very disappointing if that's what you got over a year. But because this is monthly, it's way less disappointing. And so you're taking this smaller value, but instead letting it happen 120 times over a period of 10 years. Now with this all taken care of, you can go ahead and finish this up by typing in the entire problem in your calculator. I just wanted to see some of that in between steps. When I punch that in, I got $25,472, $25,472. And so you're looking at basically doubling this money with this sort of interest rate over 120 periods spread out over 10 years. Determine the amount of an investment if $300 is invested at an interest rate of 3.5% compounded monthly for 22 years. Let's make this an OYO problem and see if it comes out okay. So unless I made a mistake, I got $647 on that one. So this is the second video, and like I said in the first, make sure that if these aren't feeling crazy comfortable, you're finding questions and asking me about them.